Welcome back to the Deep Dive. Today we're plunging into something pretty complex. It's a piece of industrial engineering most people probably never think twice about.
Right, the kind of invisible infrastructure that just makes things work.
Exactly. We're talking about what makes modern manufacturing possible, and maybe more importantly, safe.
Sounds interesting. What do we got?
We've opened up archive file number 540160. This one's from Legends Equipment, and it details the whole design, the implementation of a central vacuum system. But this isn't for your workshop floor.
Okay.
This was custom built for robotic sanding. And get this, in an automotive finish paint line. High-stakes stuff.
Ah, okay. Automotive finish prep. Yeah, that's critical.
So our mission today is to figure out why collecting dust in this specific scenario is so different and honestly far more dangerous than, just regular cleaning.
Yeah, it really sounds almost like a housekeeping task, doesn't it? Just a really big vacuum cleaner.
Right. That's what I thought at first.
Yeah. But the core problem here, the thing that drives literally every design choice in this file, it's the dust itself. It's not inert.
Not inert. Meaning,
when these robots sand modern car bodies, composites, sometimes aluminum, they create these incredibly fine particles. And that dust, it's highly combustible.
oh, okay, combustible, that changes everything.
Completely.
That immediately raises the stakes, doesn't it?
Yeah.
We're not just talking about keeping things tidy or efficient anymore.
You're designing against a potential explosion.
You absolutely cannot have combustible dust building up or near any kind of ignition source.
Which means every single part of the system, from the nozzle right on the robot all the way to the final collection bin, it has to be designed with explosion protection in mind.
Okay, let's unpack the operational side first. Picture the scene.
Yeah.
You've got this whole line, multiple robotic arms, all sanding away on car bodies.
Getting them perfect before paint. Yeah.
So this central vacuum system, it has to pull dust from all these robots, right, and funnel it somewhere central.
Often quite a distance away through, potentially really complex ductwork.
The sheer volume must be huge.
It's immense. And it's not constant. That's the tricky part. It's dynamic.
Dynamic how?
Well, think about it. You might have, say, 7 robot arms sanding 1 minute, then maybe only 3 the next.
Ah, right, depending on the workflow or the model.
Exactly. So the main exhauster, the vacuum source, it has to somehow maintain consistent suction pressure across the whole line, no matter how many collection points are actually open and drawing air.
And I saw something in the notes about robots stopping, like for tool changes.
Yeah, that's another layer. When a robot pauses, maybe to swap out its sandpaper or for maintenance, the airflow to that specific nozzle needs to shut off. Instantly.
Why instantly?
Well, if you keep pulling full suction on a connection point that's suddenly closed off at the robot end, you're just wasting a ton of energy.
Okay, makes sense. Efficiency.
And potentially you could destabilize the airflow balance for the other robots still working down the line.
So how do they manage that, shutting off airflow just to one specific robot?
It's actually pretty sophisticated. They use automated blast gates. Think of them like little automated dampers in the ductwork near each robot.
Okay, automated.
And they're directly linked to the robot's own brain. It's PLC, the program logic controller.
Ah, so they talk to each other.
Instantly, the moment the robot's PLC says, "I'm pausing sanding," it sends a signal. And snap, that local blast gate slams shut.
Wow. Seamless.
Yeah, it ensures you're only pulling air where you actually need it. And it keeps that negative pressure consistent for the robots that are running.
That makes total sense for efficiency and control. But looking at this file, the system seems, well, huge. Like maybe overkill just for the sanders?
Ah, good catch. It is oversized if you only consider the robots.
So why?
It's multifunctional. That's how they justify the scale, the investment.
Yeah.
It's also used for general plant cleaning, housekeeping in the areas around the paint line. Plus, they have hookups inside the robot cells themselves for manual cleanup when the main sanding system is down for maintenance or something.
Okay, so it needs the capacity for the continuous load from the robots, plus these intermittent, potentially high-volume manual cleaning tasks.
Exactly. Robustness and flexibility are key. It has to handle both scenarios.
So to manage that kind of dynamic plant-wide load, you must need some serious power, right? What's driving this, though?
Oh, yeah. We're talking significant horsepower, just dedicated to moving air in this hazardous dust safely.
How significant?
The heart of the system in File 54-160, it's a 30-horsepower Gardner-Denver multi-stage exhauster.
30 horsepower, just for suction.
Yep. To put that in perspective, that's about the same power as like a small smart car engine.
Wow.
But running continuously, maybe 247, just creating vacuum.
That's a really powerful image. 30 horsepower pulling fine, explosive dust out of a factory.
It is, and where you put it matters too. The file mentions strict requirements for low mounting levels.
Why low? Ceiling height issues.
Often, yeah. Sitting it into existing plants with lots of overhead pipes and structures. And noise is a huge factor with something that powerful.
Right. 30 HP must be loud.
Extremely. So to meet both the low mount need and the noise limits, they installed the exhauster inside a dedicated sound enclosure.
Ah, like a soundproof box for it.
Exactly. Solves the noise problem and helps it fit into those tight vertical spaces you find in established factories.
Okay, so we've got the Muscle 30 HP pulling power in a quiet box. But power is only half the equation, especially with combustible dust. Where does it all go?
Right. It gets pulled into the filtration and collection part of the system. They used a special type of filter unit. The file calls it a low headroom filter receiver, specifically a BRC model.
Low headroom, again for fitting into tight spots.
Precisely. It means the unit is designed to be wider rather than taller. You get maximum filter surface area packed into a profile that can fit under existing ceiling stuff, pipes, conduits, whatever. Saves valuable floor space, too.
And once the air is filtered, you've got this pile of fine, dangerous dust inside. How do you get it out safely? Without,
Creating a path for a fire or explosion. Yeah, that's where some serious safety engineering comes in. Critical stuff.
Okay. What does it involve?
The filtered material, the dust, it discharges through something called an NFPA-rated rotary airlock.
NFPA-rated National Fire Protection Association.
That's the one. That rating is crucial. It means the airlock is certified to safely handle combustible materials like this dust.
So what is a rotary airlock? How does it work?
Think of it like a heavy-duty revolving door, but sealed. It has rotating vanes inside a tight housing. Dust drops from the filter into the top pockets of the vanes.
Okay.
The vanes rotate, carrying the dust down, and then it drops out the bottom into collection drums.
But it maintains a seal.
Critically, yes. Because the vanes are always turning and sealing against the housing, there's never a direct, open path from the bottom where the drums are back up into the filter housing.
Ah, so it isolates the filter from the collection drums.
Exactly. It maintains the system's air pressure seal, but more importantly, it acts as a fire break. It prevents a flame front, what engineers call a deflagration, from traveling upwards from the drum into the main filter unit if something were to ignite down there.
That detail, the rotary airlock is a fire break, that seems absolutely vital.
It is. Non-negotiable with combustible dust.
Okay, so we're dealing with fine combustible dust, a powerful 30 HP airflow. Safety is paramount. The archive file mentions 2 critical separate layers of explosion protection. Why 2? Isn't the rotary airlock enough?
That's a really good question. It highlights why industrial safety often needs redundancy, multiple independent layers. They protect against different failure points, different scenarios.
Okay, explain. What's the first layer?
The first layer protects the filter unit itself from an internal explosion. The filter receiver was built with a side-mounted, flameless explosion relief vent.
Flameless. What does that mean?
Okay, so if an ignition happens inside that filter housing, maybe a static spark, who knows, the pressure builds incredibly fast. A standard vent would just blow open, releasing a dangerous fireball and pressure wave into the factory.
Which would be catastrophic.
Absolutely. But a flameless vent has special mesh or a ceramic element inside it. When the vent opens under pressure, the flame gets pushed through this material.
Right.
And it instantly absorbs the heat, quenches the flame, cools the gases, so only pressure is released safely, not the fire. It's this technology that allows you to safely install equipment handling combustible dust inside a building near the workers.
Got it. So the flameless vent handles an explosion inside the filter unit itself, protecting the surrounding factory area. What about the second measure?
The second measure is about isolation. It's designed to protect the rest of the system, specifically all that ductwork going back towards the robots. The system inlet, where the dirty air enters the filter unit, features an explosion isolation valve.
Okay, another valve. What does this one do?
Think of it like a high-speed safety gate or maybe an electrical circuit breaker. If sensors detect the very start of an explosion happening inside the filter housing, this valve slams shut instantly. We're talking milliseconds.
Wow.
That incredibly fast closure prevents the explosion's pressure wave and any potential flame from traveling backwards through the ducting back towards the robotic work cells.
Ah, I see. So the flameless vent contains the explosion at the filter, protecting the building externally.
Right.
And the isolation valve stops the explosion from propagating back through the pipes, protecting the production line and the robots.
Exactly.
Hmm.
Protecting two completely different, very valuable assets, the building and the production equipment personnel. It's that layered safety approach.
That level of thought, the dedication to multiple safety systems, it's really impressive.
It has to be. And it extends to longevity, too. The file even notes things like vibration isolation for the 30 HP exhauster.
Why vibration isolation?
Well, you can't have a massive piece of rotating machinery like that shaking itself to pieces or, transmitting vibrations that could affect the precision of the robotic sanding nearby. It all has to work together smoothly and reliably.
Okay, let's switch gears slightly. We've covered the power, the filtration, the critical safety hardware. What about the brains? How is this whole complex system managed efficiently day to day? Does it need constant watching?
That's where the automation and controls come in. The engineers clearly aimed for a system that could run with minimal human oversight during normal operation. Maximizing uptime is key.
And that starts with the interlocking we mentioned earlier.
Absolutely. The vacuum system's controls are tightly interlocked with the main robotic sanding system controller.
Meaning the vacuum only runs when the robots are actually sanding.
Precisely. Saves energy, reduces wear and tear, but it's also a critical safety sequence.
How so?
You never want the robots to start sanding unless the dust collection system is fully up and running at the correct negative pressure. The controls ensure that sequence. Vacuum starts, pressure stabilizes, then it gives the OK signal to the robot line.
Smart. Okay, what about maintenance then? A system like this, handling nasty dust, must need looking after. How does it signal that it needs attention?
Yeah, you can't just wait for it to fail. They built in predictive maintenance alerts.
Like what?
Well, for the filters, they installed differential pressure gauges. These constantly measure the pressure difference between the dirty side and the clean side of the filter bags.
And when the bags get clogged?
The resistance increases, the pressure difference changes. The gauges detect this and send an alert to the operators. It basically says, hey, the filters are getting dirty, time for a cleaning cycle or maybe replacement.
So you get a warning before performance drops off too much.
Exactly. Proactive, not reactive. Keeps filtration efficiency high and prevents unscheduled downtime.
And what about collecting the dust itself? Those drums must fill up.
They do. And remember those floor scales mentioned under the collection drums?
Yeah. I thought they were just for weighing the collected dust.
They do that, but they're also integrated into the control system. They act as an automatic drum full indicator.
Ah. So when the weight hits a certain point?
It triggers an alert. Tells an operator that specific drum needs to be safely removed and emptied. It streamlines the whole waste handling process and, again, crucially prevents overflows. You don't want combustible dust spilling out.
It really is a complete closed-loop system then. Power, containment, safety, and intelligent control. Looking back at this file, it lists all these features. Gardner-Denver-Hoffman exhauster, surge control for the motor, the flameless venting, the explosion isolation valve, the interlocked controls. It paints a picture of, well, necessary complexity.
Necessary is the right word.
So thinking about this whole deep dive, we started with something that sounds simple, dust collector. But what we actually found is this incredibly specialized, high-power piece of infrastructure.
Yeah, all custom designed to solve one central, frankly terrifying problem. How do
Yeah.
you continuously manage fine, explosive material right next to an active production line without, risking disaster?
It's a real lesson in the hidden engineering that goes into modern manufacturing, isn't it?
Absolutely. Things like that NFPA rating on the airlock, the 30 HP motor just for suction, the flameless vents, the isolation valves, these aren't optional extras. They are fundamental, life-saving engineering choices.
Without that level of design, the production line either couldn't operate safely, according to regulations.
Or it would be running with an unacceptable level of risk. Safety in this kind of environment is literally what enables production and efficiency. They're intertwined.
So true. It makes you think.
Yeah.
The next time you admire a brand new car with that perfect paint finish, take a second. Think about the intense, completely unseen layers of engineering explosion-proof, highly automated, that were needed just to prepare the surface, before paint even came near it.
All those flameless vents and rotary airlocks and PLC interlocks working silently in the background.
Exactly.
Yeah.
Which leads to a final thought for you listening. What other manufacturing processes, maybe handling volatile chemicals or extreme heat, or other specialized types of dust do you think require this same hidden level of complex, interlocked, safety-critical design? Something to maybe mull over.
Definitely food for thought.
We'll leave you with that. Catch you next time for another deep dive.